Infinite geometric series. So again, we're dealing with geometric series, but we're going to talk about a very special type of geometric series. So imagine you have a cake. These cakes are amazing. And you cut the cake in half, and you give one half to somebody. Why? Because you're just that kind of person. Okay? Then, you cut the remaining piece in half and give one to somebody else. How big is the portion that you're giving them? A quarter. Okay? If you keep cutting the cake in half, how many people can you feed? Would you have distributed the entire cake? Okay, so first of all, you give the first person a half, you give the second person a quarter. What do you give the next person? An eighth, because you cut the quarter in half, which is 1/8. The next person you give 1/16, then 1/32, 1/64, and so forth. Okay, my question for you is, how long can you keep doing this? Can you keep doing it infinitely? Can we keep taking numbers and cutting them in half? No. Even if I gave you like an insanely large number, could you not cut it in half again? You could. Doesn't matter how small the number is, you still cut it in half. Yeah, so how many people then could you feed? So what would you call that in math? Infinite. If you feed an infinite amount of people, will you get through the whole cake then?
No.
It'd be like a ball of people left.
Okay. If we talk about infinity though, if we do this for infinity long, will we eventually get to our whole cake?
No.
The answer is yes. If, only if, you do this for infinite long. You do this forever and ever and ever, and then you think you're done, you're still doing it forever and longer. Okay? Infinite amount of time, and yes, you will. But only in that concept of infinity, which we have a hard time grasping in our head, right? Because we like things finite. The idea of numbers getting larger or infinity it's hard to actually put our head around that. So it's the same problem has been like if I walk half the distance, will I ever reach the wall? The same idea. How long could I do that forever? I could keep going forever. And I only actually reach the wall if I do that forever. Okay. So, yeah, infinite along. So I know your head hurts, doesn't it? No? It should. It should hurt. So we're dealing with this series that we just looked at. And if we make this a series, if we add all of these together for infinite along, let's find out if it actually does add to something. To prove it, I'm going to use mathematics. Okay, I'm going to prove that if I do this for infinite long, then it's going to add to one cake. All those pieces together. Okay, how is that? Well, my first term is a half. Agreed? Common ratio is a half? Yes. Okay, so you recognize this formula? Yes. Term 1 times r to the n minus 1 over r minus 1. It's on your formula sheet for geometric formula. Okay, so what's going on here? Well, first, a half minus 1 is equal to negative a half. Do you agree with that? So here, a half minus 1 equals negative a half. That's what happened here. Yes, good. Now, what happens if I take 1/2 and I divide it by negative a half? It cancels, but we're still left with a negative. Okay, we're still left with that negative. And now I'm going to distribute that negative in, and that's how we get the formula. The negative 1 becomes a positive 1, so it's moved out front, and then the 1/2 to the n becomes a negative 1/2 to the n. So we haven't actually answered anything here. But this is what we're going to do. I want you to grab your calculators. Yep. And I want to prove to you that this will add to infinity, add to 1 cake eventually. So what we're going to do is we're going to choose some n values. So start with a smaller n value. How many pieces do you want to give away at cake? 5? Sure, let's do 5. 1 minus, bracket, 1/2 to the power of 5. Tell me what fraction of the cake does that add to? You gave away 5 pieces. That's what we had above. 1/4, 1/2, 32, 1/8. So was it the whole cake? No, it's 31. It is 32 pieces. Equal pieces. Okay? Okay, give me another number. More, larger. How many people do you want to feed now?
12.
12. I love it. Okay, 12 people we're feeding. 1 minus 1/2 to the power of 12. Does that equal 1? Not quite. It's 4,095 out of 4,096. There's still a piece that we can cut in half. Okay, give me a larger number to feed.
46.
Pardon me? 35, 46. Okay, doesn't matter. Boom! Okay, it didn't take long actually for us to get to that 1. So what happens is it actually 1 yet? Not really. Your calculator, this number is so small, so small, it's counting it as what? 1 minus what number would give you 1? 1 minus what equals 1?
0.
0. It's so tiny, it's basically approaching 0. And so actually once we put it to the power infinity, because you're having 1 over 2 to the power of a very large number, you get 1 over a huge number. It's huge. Okay? It's so big that as we approach infinity, it actually equals 0. Okay? So this is becoming 0. All right, back to our notes. So this actually approaches 0. So the infinite sum of this problem is 1. We actually cut it, and our calculators, would you agree that they're limited? So yeah, it told you that's equal to 1. You know that it's not 1, right? You know that. That shouldn't have been 1. It should have been a really close number to 1. And our calculators are followed. And it actually only adds to 1 when we do it to infinity. But our calculators can only do numbers so small. All right. So so this is only for geometric sequences. There's 2 types of geometric infinite series. I should say series, not sequences. Convergent, divergent. Reminds you of a book, probably. No? Sorry. Or a movie for some of you. There are 2 types of infinite series, convergent and divergent. So what's in a convergent? And a convergent is the really important one that we're going to talk about the most. The convergent series occurs when the common ratio falls between -1 and 1. So on a number line, if I think of numbers between -1 and 1, and I should say not including 0. Why? What if my common ratio was 0? Make this larger for those at the back. If my common ratio was 0, what would the sequence be? Would it be broken? Okay, say our first term was 2 and our common ratio is 0. What's my next term? If my common ratio is 0, I'm multiplying by 0. 0. What would be the next term? All right. So is that even geometric? Well, Yeah, I guess so. It is. Oh, I guess it is technically convergent. It would be, because what would that, if we add all these terms together for infinity long, what would it add to? 2. It's just be a really boring sequence. Yeah. So actually, including 0, but you're never gonna see 0. I'm gonna erase the including 0. You're never gonna see that. It's so boring. Okay. It does actually. So a convergent series, guys, is when it actually has an infinite sum. Is that, and how do we spot it? Well, we spot it because the common ratio is between -1 and 1, but not including -1 and 1. We'll talk about why in a second. So why numbers between -1 and 1? Well, if our common ratios between -1 and 1 are actually, what happens to our sequence is it's actually shrinking. It's getting smaller. Looking at this one, what's our common ratio, this first example? It's half, right? We're multiplying by a half each time. Our common ratio is 1/2. Is that between -1 and 1? Yeah, right? Numbers between -1 or 1 are fractions and decimals. As long as your fraction is the numerator is smaller than the denominator. 2/3, 5/6, right? Those are numbers between -1 and 1. So notice in the sequence here, 4, 2, 1, 1/2, 1/4, the numbers are getting smaller. And so if we add these up into infinity, sooner or later it's going to approach what? The last term, 0. And so we have an actual sum. We can find the sum of the sequence, and we're going to today. So that's convergent. The next one, what's the common ratio? Close. Okay, it goes minus, plus, minus, plus. So the common ratio is a negative. And then divide your numerators to get the numerator. 80 divided by 40 is 2. 9 divided by 3, 3. So -2/3. Okay. So is that between -1 and 1? Yeah. Okay. So that would be a convergent series. If your common ratio is 1, then your sequence looks like this. Okay, just a side note, this would actually not be convergent. This is divergent. Okay. Theoretically, this could also be an arithmetic sequence because you're adding what each time? 0, common difference of 0. Okay, or geometric, common ratio of 1. So it can't include 1 and -1 because are those numbers getting smaller? No. So it's not going to reach an infinite sum. Okay, so divergent occurs when the common ratio is greater than 1 or equal to, I guess we can add that, or less than or equal to -1. The series does not approach some number if that's the case. So what's the common ratio in this example? 2. And what's the common ratio in this one? -2. So those, either of those don't fall between -1 and 1. Let's look at the last page. Yay. Okay, I'd like you to give this a try. Classify each as either convergent or divergent. Convergent or divergent for the first one? Okay, so when it's divergent, it's not going to add to some number. This is going to add to infinity, actually. The numbers are getting larger. Next one, what's common ratio? 1/4, so it is convergent. Converges. Okay. Last one, common ratio is 1/2, so therefore it is, it's like laid out for you. Convergent. So if it's convergent, how do we find the infinite sum? Here's my, it's on the formula sheet. We are not going to prove this formula. It has to do with the front page that we looked at. when we did that approaching 0 type of stuff. Yeah, we're not going to prove this. We're just going to use this formula. If you want the proof, you could either talk to me, I could show it to you, or the textbook. Okay. So that's our formula. It's really simple, hey? First term divided by 1 minus r. That's it. It's that simple. Find the sum of the following infinite series. So, what's my first term? Quarter. What's my common ratio? 1/4. So infinite sum equals term 1 over 1 minus r. Here's some fun with fractions. Yeah. 1/4 divided by 1 minus 1/4. Now, if you were to enter this into your calculator, you would want to have brackets around your numerator and around your denominator. Okay? But if you want to just use your head, we could do that too. What is 1 minus 1/4? If I take away 1/4, how many quarters are left over? 3/4. When you divide fractions, it's the same thing as keep. Remember, it's, I think, okay, I heard it last minute. Keep, flip, switch. Does that sound familiar? Okay, or multiply by the reciprocal, or kiss and flip. Right? Kiss and flip the second fraction. Kiss and flip. So we can reduce the 4s. Because there's 4 on the numerator, 4 on the denominator can cancel. We're left with 1/3. Calculator, I'll show you calculator. That's okay. Okay, so on your calculator, we had brackets, 1/4, divided by bracket 1 minus 1/4. And then that equals 1/3. Math, enter, enter. Good times. Fun. Okay, one more. Infinite sum. Term 1 over 1 minus 1/3. So again, if you were to enter this in your calculator, the biggest thing you need to know is that if it's a binomial ever, you need brackets. BEDMAS will not prevail on your calculator, right? Or actually, BEDMAS is happening on your calculator, and so if you don't tell to have the brackets, it'll do 3 divided by 1 and then subtract 1/3, as opposed to 1 minus 1/3 and then 3 divided by that. If you want to use your head, 1 minus 1/3 is 2/3. And flip, kiss and flip. 3 times 3 over 2 equals 9 over 2. Okay, on your calculator, 3 divided by bracket 1 minus 1/3. Okay, that's it. That's the lesson. Did I not tell you that you'd have 30 minutes? It's a pretty good estimate, hey? It's like I already did this today. Almost.